Thank you, Alejandro. So we need to move on now to the next speaker. So the next speaker is Armando Solar-Lezama. He is a professor here at CSAIL. If you were here yesterday, he was on my panel, on the international panel, and I believe now he's going to explain more about his research and what he has been doing in CSAIL. So he's leading a group in the computer science laboratory. So he's getting his microphone down now, but.
All right, so sorry for the delay. So I want to tell you a little bit about some of the work we do. So my group originally focused on the area of program synthesis. This is an area that had been kind of forgotten within the programming languages community until maybe now about 15 years ago, when we started doing work in this area. And the high-level idea is to be able to generate generally small pieces of code that do things that you want. And in particular, we've developed a lot of techniques within my group that were able to take, on the one hand, a set of behavioral constraints, restrictions on how you actually expect a program to act when presented with different inputs, together with structural constraints that tell you what kind of program you're looking for. This might be in the form of just a set of components that have to be used for the program, or they might be in the form of just input-output examples. For this input, I want this output. And turned out to actually work pretty well. Today, we can synthesize relatively complicated data structure manipulations, for example, from high-level specifications, and actually verify that they're correct. If you use Excel, there's even a functionality there called flash fill that actually one of my students who worked on in collaboration with researchers at MSR that is able to take some examples of some string transformations and generalize them to a program that it can then apply to your whole spreadsheet. And there's other settings like bit-level manipulations, the kind that happen, for example, in network protocols, that we can actually synthesize pretty effectively. But a few years ago, actually, one of my students realized that you could do a lot of other things with this kind of techniques. Once you have the ability to generate little pieces of code from their behavioral constraints, you could actually attack problems that look nothing like program synthesis problems. For example, this was one of the first problems in the category that we started looking at, and we started this work in collaboration with Josh Tenenbaum. So if you look at these two pictures, and then you ask a person, OK, which of these pictures is like the first two? Right? Any person can just look at that and say, well, obviously, the one at the bottom looks more like the two on the left compared to the one on the top, right? But it turns out, if you try to train a machine learning system to solve these kind of problems, it's actually kind of hard. It's actually kind of hard to generalize from these two pictures. On the other hand, if you ask a person, well, why do you think this picture at the bottom is like the other two? A person can easily tell you, well, because you have some kind of blob, and then you have a bigger version of the blob. Or maybe they might characterize it as you have some kind of blob, and then you have a smaller version of that blob. Well, we can actually codify that as a little program that says, well, go to some position, draw a shape, and then draw a smaller version of that shape. And so by framing this as a program synthesis problem, essentially find me a program that could explain the two pictures that I observe, you can actually solve these problems pretty effectively. And so we started actually looking at other domains where you could actually do similar things. For example, one of the domains that we've been playing with is the domain of linguistics, where one of the things that linguists are really interested in are codifying language morphology rules. How does a language, for example, take a singular of a word and convert it into a plural? Or how do you take the present tense and convert it into the past tense, right? And this is the sort of thing where, sure, you could take a big corpus of words, say in English, and train a traditional machine learning algorithm to predict how the present tense is going to turn into the past tense, or how the singular is going to turn into a plural. The problem with that kind of black box model is it's not really going to tell you much about the structure of the language, right? On the other hand, linguists have developed notations and formalisms to describe exactly these kind of rules, that if you have a description in this formalism, you can actually then, for example, look at relationships between languages, be able to say something about the commonalities or the differences between languages. You can actually look at those rules and say, yes, this makes sense based on what I know about where this language comes from. And so again, you can actually frame that as a program synthesis problem, where now your programming language is this language, this formal notation that linguists have used all along. And so what that made us realize is that there's actually this very close relationship between more traditional machine learning and these program synthesis techniques that we had been working on for several years at that point, right? In particular, if you think about the traditional machine learning problem, basically you have a big data set. You have, let's say, if you're trying to train a function, you have a bunch of inputs and outputs. And with that, you trained your learned model so that given some new input, it's going to be able to produce the new output. And what you hope is that you'll even be able to generalize to things that you've never seen before. Well, a lot of the work that we had done in program synthesis actually looked very similar, with a few important differences. First of all, generally, we don't think in terms of big data. We tend to think in terms of the kind of small numbers of examples that a person might give you. So we're not talking about millions of data points. We're talking about 2 or 3, in some cases maybe even 1. Now, how in the world do you learn something from 1 or 2 examples? Well, you do that by having very strong priors on the kind of programs that you actually are looking for. You do that by knowing a lot about the structure of the problem, by knowing a lot about high-level properties that you expect the solution to have. And so the question we had then is, could we actually leverage these kind of techniques for more of these problems? And in particular, is there a fruitful combination between the kind of things that machine learning is good at, namely learning from a lot of data, namely dealing with more quantitative objectives, but also the kind of things that our program synthesis techniques were good at? Things like dealing with structure, being able to guarantee properties, and being able to leverage small amount of data. And this was actually quite interesting because on the one hand, we are really coming from very different worlds, right? On the one hand, modern machine learning is all about optimization. There's a lot about reasoning in terms of probabilities. Real numbers tend to be scary for people coming from my side of the world in programming systems. On the other hand, we bring in a lot of very powerful machinery for formal reasoning, for deduction. We have a long tradition of focusing on things like structure and modularity, abstraction and compositionality that have tended not to play such a prominent role in the machine learning setting. And so I want to show you a couple of projects that we're working on where we're trying to explore this intersection. And we're trying to look at what can you do when you bring together, on the one hand, the ability of modern machine learning to assign meaning to very unstructured inputs, its ability to reason in settings where you might have a lot of noise, but on the other hand, where you're able to bring in the symbolic reasoning and be able to do the kind of inference that the kind of techniques that we're used to allow you to do. So this was a paper, for example, that we presented at NeurIPS in 2018. And what we were looking for there was could we interpret hand drawings? And in particular, could we look at pictures like this and not just capture the fact that, OK, yeah, there's some squares and some circles and some lines, but really capture the underlying logic behind these diagrams. Capture it in a way that allows you, for example, to generalize, right? To say, well, here the person drew a 3x3 grid, but we could just generalize that to a 4x4 grid, or to a 5x5 grid, or to a 100x100 grid, right? This is the kind of generalization that symbolic reasoning is very good at allowing you to do. So at the same time, symbolic reasoning is not so good at dealing with very unstructured, pixel-level, poorly drawn hand drawings. Right? And so the idea in this case was that if we can set a pipeline where, on the one hand, you start with a learned model that you learned from a lot of data that is able to extract from that very unstructured input, that is able to extract symbols that now we can manipulate. Now we can reason at the symbol level. And now we can actually synthesize something that is actually in the form of a program that gives us some insight as to what those symbols are actually doing, right? Or to put it in pictures, you want to go from a very unstructured, fuzzy representation to something that is much more formal, that then allows you to actually do the kind of manipulation that you need in order to get the final product that you want. So essentially, what we wanted in this case was to be able to go from these hand-drawn figures to a program that actually describes the logic underlying that diagram, that allows you to have that kind of generalization. So the basic strategy here was that we started with a combination of neural network and search to actually go from the hand-drawn drawing to a symbolic representation of the hand-drawn drawing. This is not yet capturing much of the logic behind the diagram. It's simply recognizing, oh, there's a circle here, there's a circle there, there's a line here, there's a line there. But now that we're in the world of symbols, now we can use those symbols to actually try to extract some higher level structure. In this case, those symbols now become our specification, right? What we're looking for is now a program that can generate symbols like the ones that the neural network observed, right? And so in doing that, the system is able to capture not just looping behavior, but it's also able to capture, for example, symmetries. The fact that some part of the drawing is like some other part of the drawing, just mapped and translated in a particular way. And so the idea is that you're able to go from pixels to symbols to a much higher level representation of those symbols. And on the one hand, one thing that allows you to do is it allows you to generalize these drawings, to be able to ask, well, how would this drawing look like if it were bigger, if it had more elements? Now, one of the things that is particularly interesting here is that generalization that you're doing really from a single image, right? You're trying to capture a pattern from a single image, is very much driven by the underlying language that you have to describe your drawing, this underlying programming language. And so, for example, one of the things that we find is it's not always perfect. In some cases, it makes generalizations that are not exactly what you would expect, right? Now, what's wrong with that particular generalization? Well, there's a particular feature of that drawing, which is the original drawing, the one in white, that the lines are attached to the circle, right? There's arrows coming out of one circle into another circle. The problem is our language for drawing these pictures does not have a notion of an arrow going from one element to another element. Instead, it has a notion of an arrow going from one set of coordinates to another set of coordinates. And so what that means is that the generalization it tries to do is not in terms of those lines being attached to the circle. It is instead in terms of the lines following a particular pattern in their initial coordinates, right? So what we see here is actually this very interesting thing that the language, the underlying language that we have, is actually what drives the generalization that we're going to get. Another thing that is actually quite interesting in this case is that we can actually take this symbolic layer and use it to make up for errors at the perception level. So just by changing a little bit how you frame the synthesis problem and giving some weight to the cleanliness or the regularity of the program that you get, you can actually see examples like the one on the top. So given that hand drawing at the left, the neural network basically saw that line in the last circle and said, yeah, that kind of looks like an arrow. And if you were to look at that in isolation, you could be forgiven for thinking, yeah, that could sort of be an arrow, right? In other contexts, you could say that that line is an arrow. There's that other line coming out of it in kind of an unusual angle. But if we look at the program that that figure in the middle represents, it's actually a bigger program, a more complicated program than the one represented by the figure in the right. And so what the synthesizer is actually able to do is play off that trade-off to say, well, yes, I could give you this very complicated program, but I could also give you this simpler program that also almost matches what the neural network gave you, right? And so we can actually now do these trade-offs, having this much higher level symbolic representation of the drawing, having this global view of what those symbols represent. More recently, we've actually been pushing the same idea into the domain of computer-aided design. It turns out that the same kind of thing that is desirable for these 2D hand drawings is very desirable when you're dealing with 3D shapes. When you're dealing, for example, with, let's say you have a machined part that comes from a machine from before the CAD era. It comes from a machine maybe that for which you do not have nice high-level CAD design for it. But you nevertheless want to take this machine part and you want to make a copy of it. Not just make a copy of it. You want to modify it. You want to make it better. Well, it'd be really good if you could actually get not just the surface geometry of this part, but the underlying logic of what was the series of operations that gave you this part. And so we actually had a paper in 2018 also looking at this problem. And we've been continuing to push in this area. Now, once again, just like in the case of the hand drawings before, one of the things that is very, very crucial is the underlying language that you use to describe those things. Because from the same data, from the same input, you can reach very different conclusions depending on what your underlying language looks like. And so one of the things we realized is that people are actually pretty good at coming up with good abstractions by looking at other problems that have come in the past. So for example, if I show you a list like this, and I tell you, OK, what is the function that mapped the input list to the output list? Who knows? It's not so clear, right? On the other hand, if I show you something like this, right? Can anybody tell me what the pattern is here? Yeah, exactly. I'm just swapping the first and last elements, right? Especially the middle one kind of makes it pretty clear, right? And what about this function? What is this function doing? Right? The one at the bottom should probably key you in on what this is doing. Yeah, it's just sorting, right? It's just running them in order, right? And once you have those two things in mind, right, you can look at this and you can see, oh, I'm just sorting the list and then swapping the first and last element, right? If you know that those two are components that are available to you, if you know that those two are just operations that you can use, then it's very clear that this is just a composition of those operations, right? But that's an inference step that is actually pretty hard for humans. That's actually pretty hard for machines to do completely automatically. Yes?
Sorry, it could also be a shift left, right?
It could be many things, right? That's the point. It could be there's an infinite set of functions that could map this to this. But if you're viewing this from the perspective of just these two functions that I showed you just before, then all of a sudden that limits the things that you might actually consider for this, right? And so when we look at a lot of these problems, the way we actually solve them is you have some requirement. I want a function that maps the input to the output. And just by looking at that requirement, the problem is extremely ambiguous. There's an infinite set of functions that could give you that mapping. But if I give you a particular domain-specific language, right, a particular set of operations, and I also give you a prior on that space of possible programs that you could actually use, then all of a sudden the problem becomes very well defined. You're looking for the program that is most likely within this language to give you the behavior that you observe. And all of a sudden that allows you to make very powerful inferences. And so the big question is, well, could we learn this? Could we have a machine actually figure those out? And well, the short answer is yes, we can, and it's actually pretty cool. Given that we have only 40 seconds, I think, I am going to just jump to the punchline and tell you that there are some cool techniques that go into making this happen. And we can actually do some pretty interesting things. For example, we can start with a very low-level language for Lisp manipulations. Basically, think about 1960s Lisp. Just car, coulter, basic ability to construct recursive functions. But then by giving the system a corpus of problems, what the system is able to do is infer higher-level functions that are able to do things like, oh, find the maximum element in the list. That seems to be something that is used a lot in these programs. Or find whether the list contains a particular element. From this corpus, it's able to not only discover these symbols, but also discover a distribution over these symbols that then allows you, given very little data, to actually infer a program that looks like the programs that generated that sample corpus. I just want to show you very quickly another sort of neat domain where we were able to do something interesting. So the idea was to start with a very, very simple language for drawing graphics. This is this logo formalism where you basically have, move the cursor somewhere, pen up, pen down, and basic looping and arithmetic. And then you give it a corpus of drawings like this. You don't actually show the system the programs that generated those drawings. You just show it, here's a bunch of drawings that I need to be able to generate. Right? And from those, what the system is able to do is bootstrap from the programs that are able to solve the simplest programs in this corpus, and then identifying common elements, common semantic behavior in these programs, even if they look very different, but inferring common semantic behavior that then allows you to extract from that primitives for doing things like drawing circles and spirals and different kinds of curves, but also higher level compositions. For example, higher order functions that are able to say, give me a function that will draw some kind of picture, and then I will draw, and then give me an n, and I will draw you a radially symmetric repetition of that picture. So we're able to discover these higher level concepts by synthesizing, starting from simpler programs, and then doing symbolic analysis to actually identifying the common structure behind this that is actually able to give you the behavior that you want, right? And so these are just a couple of simple examples showing you the kind of things that you can do when you bring in this combination of symbolic reasoning, and you're able to bring to bear the power of modern symbolic reasoning techniques, but without losing the ability of modern machine learning to actually discover intricate patterns, to actually be able to learn very complex distributions over very complex objects, and the ability to assign meaning to very unstructured input. So by bringing the two together, you can do things that you wouldn't be able to do just by doing one or the other. So I think this is a good place to stop. And I guess now we have questions.
Thank you, Armando. We have just quick time for one question, if anybody is ready.
Oh, thank you so much for the presentation. Is there any metric to understand if the most probable answer is correct? The most likely answer is correct?
Yes. So for a lot of these techniques, you want to have some kind of background distribution. You actually want to have a test set where you can actually test the solutions that you generate to be able to say whether these solutions are actually the correct solution that the user intended and not just something that, yes, happens to match the data, but is not the thing you want. One of the things that is powerful about these kind of techniques is that you can often generate not just the one solution, but you can actually characterize the space of solutions and, for example, generate tests that will disambiguate between them and will allow you to discover which one is actually the right one. All right, thank you.